Good day, ladies and gentlemen, and welcome to today's American Society of Civil Engineers webcast, hosted by the Geo-Institute, titled Computational Geotechnics Technical Committee. To submit a question or comment at any time during the webcast, please click on the Ask Question button at the bottom of your screen. At this time, it is my pleasure to turn the floor over to your host, Usama Shamy. Sir, the floor is yours.
Hello, everyone. My name is Usama Shamy. I am from Southern Methodist University in Dallas, Texas, and I am the Vice Chair of the Computational Geotechnics Technical Committee. The Chair, Professor Jose Andrade, is available with us, and he's going to give a presentation later on today. We had a total of 5 presentations, and before we give you more details about the presentations, I would like to acknowledge our gold sponsor, Hayward Baker. As you all know, Hayward Baker is North America's leader in geotechnical solutions, with a network of local offices across North America, each with direct access to the largest geotechnical knowledge base in the industry. Hayward Baker is ready to respond with the optimal solution wherever the location, whatever the size, whenever required. Solutions include foundation support, settlement control, ground improvement, slope stabilization, underpinning, excavation shoring, earth retention, seismic liquefaction mitigation, groundwater control, and environmental remediation. Hayward Baker is part of the Connected Companies of Color, a multinational organization providing geotechnical construction solutions throughout the world. We greatly appreciate the support from Hayward Baker for our activities today. The list of presentations, we have 5 presentations, and 6 speakers will perform those presentations. And we have a spectrum of expertise. We have speakers from the industry as well as speakers from academia to enrich the content of the presentation or the webinar today. So this is the order of the presentations. We have a presentation, Reliability-Based Geotechnical Design Using Everyday Tools by Jomâa bin Hassan and Professor Griffiths. And we have also the second presentation is Validation and Verification in Geomechanics by Professor Mourad Zeghal of RBI, and in co-authors Majid, Manzari, and Bruce Kutter. Our third presentation is going to be presented by 2 speakers, Professor Hryciw and Professor Jose Andrade. It's on image analysis, systems and computational methods to characterize coarse-grained soils for engineering practice and for construction of DEM cluster models. The fourth presentation is by myself. It's on seismic soil foundation structure interaction, new insight. And last but not least is a presentation on geotechnical numerical modeling best practices guidelines by Nicolas Oettle. So without any further ado, I would like to start the first presentation, and I will leave each presenter to give a brief introduction about himself for the audience to know the expertise, his expertise.
Okay, thank you, Usama. This is Jomâa bin Hassine. Can everyone hear me? Okay, I hope so. My name is Jomâa bin Hassine, and my co-author is Dr. Griffiths from the Colorado School of Mines. I am a civil engineer with about 30 years of experience in geotechnical and structural, And I'm also doing a Ph.D. thesis at Colorado School of Mines, and Dr. Griffiths is my professor. Today's presentation, I wanted to focus on some everyday tools that we find on our computers to do some, I think, fantastic work, and maybe compare our results to common practice by designers. And so the title of my presentation there is Reliability-Based Geotechnical Design Using Everyday Tools. And the outline of this, what I'm going to talk about is I'm basically going to talk about some introductory concepts for the design of what's happening nowadays. Also some introductory concepts on reliability and risk, some limit states, and I will talk a little bit about this framework. It's called Direct Reliability-Based Design, and explain how that is feasible and could be done on common machines. And also I will talk a little bit about some applications, talk about some benefits, and hopefully we learn from each other. The first thing I want to talk about is the concept of risk, and risk is not really a probability of failure. It is not how likely something is going to collapse. It is a combination of that likelihood and also the consequence of that event. So it's important to remember that risk is always has a cost or a consequence component. And also I mentioned something about consequence of failure. It is not something that could be measured readily. It could be dependent on how society views something. It is how critical or bad for the society. So this slide here is from 1987 and shows what society has typically accepted as being acceptable risk. And you could see that, the consequence, if it's going to be threatening lives or then the probability of failure would have to be a lot lower. So the important thing to remember from this slide is that consequence of failure and how society views it is different from in different regions of the world. Talking about how the engineers have been designing structures, and this is probably very basic common knowledge for a lot of the audience here, but it is good to go over it and just to explain the differences. Historically, the allowable stress design or the working stress design method was used in many fields, structural steel design or geotechnical to this day that is still used in some areas. And this method is mostly based on experience. So if you assign one, it's a global factor of safety, and experience has shown that the factor of safety of so-and-so has shown good results, so that is adopted. But it doesn't have a lot of probabilistic underpinnings. The current nowadays design standards are using the load and resistance factor design or the limit state design approach, and there the factors are split between the resistance and the load. So you could assign the uncertainty differently depending whether you're talking about load or resistance. So that is a more refined approach, and those factors are determined through studies and more code calibrations. So the standards, when they specify all these load factors and resistance factors, they are targeting a certain reliability in the design. So it is probabilistic in that sense, but it is still called semi-probabilistic because if your design is outside those assumptions, then you cannot say that I achieved this reliability, this target reliability for that design. So you will have to do additional studies. What we're proposing and what I'm talking about today is a method that doesn't use any factors. It's fully probabilistic. And it is used, it's basically Monte Carlo simulations and Bayesian analysis of those statistics. And it is used right now to come up with factors that are used in the standards for loads and for the resistance. So that's what's called code calibration. But what I'm suggesting today is that this method could actually be used in actual design, and the tools are available to engineers to actually do that. And even if the design standards may not be allowing you to do that, let's say, at least if you implement this, you can compare your design. How is it? Is your design really conservative? Is it optimistic? Things like that. So, but probably in the future, it probably will move that way with these tools. Just for reference, these are typical factors of safety for the low stress design. These are, for example, you can see that for serviceability limit states, usually the factor is 1. It's like, comparing what is the tolerable to what is what you calculate at settlement, for example, and what is tolerable. So if that comparison agrees, then it's fine. There's no factor of safety essentially there. For bearing capacity and ultimate limit states, there is a factor of safety, global factor of safety, like 1.25 to 2 for overall stability. Talking about also some concepts here for reliability index. When you say I'm designing for a target reliability index, what is that? And how does it compare to probability of failure? There is a one-to-one relationship between these two. Probability of failure is, as you can imagine, is something very small, a number like 0.00301 or something like that, to the power minus 3. Reliability index, it's the equation that is shown on the slide, is 1 minus the standard normal probability distribution of the beta. So there is a one-to-one relationship, and this table shows some approximate comparisons for comparing the probability of failure to reliability index. And the reliability index, you can see it varies between, let's say, 1 to 5. It's something that's probably could be tempted, you can say, like a factor of safety, but it is not a factor of safety. So reliability index is not, it's different from the factor of safety. Between reliability index and the factor of safety, as we know it, like a global factor of safety, there is not a unique relationship. This graph here, for normal distributions, if you assume that the factor of safety is normally distributed, it shows the relationship between, approximate relationship between the reliability index and the factor of safety. I hope you will have a copy of the slides, and you probably could study them at your own pace. Here, I will not read out the slides. Just also for reference, this is from the European norms, Eurocodes. For a 50-year reference period, this is the target reliability index. And you could see here that it is the consequence of failure is being reflected in this. Like, the consequence of failure, the top row, it's small, some, and moderate, and great. And then also the cost of implementing safety measures. So also there, if it is high or moderate or low. Commonly, standards right now in the US and Europe, the target reliability index for ultimate limit states is around 3 point something. Okay. And it's different, a little bit different from different standards, and this is normal. As these standards are calibrated differently, you could come up with something slightly different, but that's the range, is about 3 for ultimate limit states. I want to talk about the current design, the foundation design practice, what happens currently. The task is split between the geotechnical engineer and structural or foundation designer. They'll start with some input. Typically, for example, the geotech engineer is given some information. It's quite limited. Maybe the type of structure. Sometimes they will give you the maximum load. Sometimes the client would specify the limits on settlement, differential or total. And we give you some geotechnical parameters, like in a geotechnical investigation, you can come up with some parameters. The process, the geotech engineer, what typically done right now is they will estimate the ultimate bank capacity from a deterministic approach. And then they would reduce that bank capacity to account for the serviceability mistakes, which are like settlements. And so they will specify that as the bank capacity, and it would meet the settlement and the bank capacity criteria. But you know what? At the end here, what you end up with is something that has no probabilistic basis. Okay. What I'm suggesting in this approach is a fully probabilistic method, and the process I would like to suggest is the task is still going to be split between the geotech engineer and the foundation designer. They would still start with some type of structure and the limited information that we typically have, and the criteria for serviceability limit states and things like that. But the geotech engineer, now the focus of the geotech engineer should be to assess the variability of the geotechnical design parameters. Like you have different limit states in this design, and each limit state would involve some random variables. The geotech engineer, the focus of that engineer should be to assess the uncertainty in those parameters, and in addition to the characterization and the typical, all the geotechnical reports that you've been seeing. But then the foundation designer would pick up with this method and come up with design that meets all the limit states to the target reliability that is intended in the design. And this is a fully probabilistic approach. So I'd like to describe the steps that are involved in this approach, and you can read the slide here at your leisure. But basically, you need to define define the problem, the parameters, the limit states you're talking about. Okay. For each limit state, of course, you're going to have the performance function, which is like your equation. You're going to select that as a designer. This equation is more appropriate for this case than this, so that's a judgment call on the designer. But so that's your limit state. And then for each of these limit states, we're going to generate realizations in a Monte Carlo simulation framework. Realizations, like you're going to start, I don't know how many, but I will go over later how many realizations probably you're going to need. And then you're going to do some statistics on that and come up with a design. From all these limit states, you're going to come up with an optimal design, which is the least cost design, meeting all the limit states that are being considered. Again, this slide is the same approach, and I'm not going to go through it again. So to summarize here, for this method, you're not going to need any factors, no partial or global factors. You're going to define your performance function, and that's a judgment call by the engineer. And so that is some judgment left to the engineers to make that choice. And you need the uncertainties for the random variables. So that input comes from the geotech engineer. So if you have some idea about, if you want to make some assumptions on the cross correlations between the random variables, this is also possible here in this method. And of course, you need the target reliability of for all these limit states. So that is a critical starting point. And if the consequence of failure, if you know that, you could adjust this to reflect that. This is the key formula used in this method. It's based on the Bayes conditional probability rule. In this approach, we're randomizing all the select random variables that you pick. Okay, but also you randomize some design parameters. For example, for a foundation, you could be randomizing the depth D and the B width B of the foundation. Okay, and those are randomized, but they have a uniform distribution. It's just to include them in the process. So when you do a simulation, it's just one run of this Monte Carlo simulation, and you run the simulation for all the foreseeable combinations that you want to consider for this design. For example, your foundation, let's say it's going to be between, you think it's going to be between 5 and 12 feet in width or something like that. So you can pick 5, 6, 7 to 12, and you're going to pick uniformly from those selections. And so that step is included in the simulation, and this equation will actually determine for each of these combination of parameters, that's B and D. You could have only one parameter if your design is only designing for width only, for example. It will tell you for that combination whether you're meeting the target, the probability of failure or not. And at the end, you're going to have the end result will be all the combinations of B and D that meet your target probability of failure. To go into the question of how many realizations you need, there are some suggested formulas, and they're listed here, and with the references. We're talking about, if we're talking about, let's say, probability of failure for 0.001, we're probably talking maybe like 500,000, 300,000, and sometimes even if you have to run millions of realizations, with nowadays computers, you could do that in a couple of minutes. So it's not a big challenge like not like before. What are common everyday tools that I'm suggesting here? And there are definitely many other tools, but Excel will probably come to mind because it's on every machine. Also, I can think of MATLAB and MathCAD. MATLAB is quite performs very well. MathCAD, I see it as to present calculations. It's very presentable. Python, it's open source, and also it is. I think it's known for interoperability or something like that. So, but what I would recommend maybe for the Excel, what I'm doing right now with Excel is actually using it with VBA, Visual Basic, to do the calculations, and the Excel will do a lot of the graphing. So some examples here. I don't know how much time I have. I think I have. Okay, some examples for bearing capacity. I've been working in renewable energy for the last 10 years, so this is a good example. Bearing capacity of wind turbine foundation. This is some example from the Excel tool, and if you can look at there, you can define all your uniform, design decision parameters, the selections for you want to come select from, and here you could see 2 minutes. So I'm gonna slide through them very quickly, but you can go through the slides later. Here, for example, a scatter plot showing the fail cases at the bottom, and you can also consider cost variations. Here at the end, you can select the designs that work, that meet the target probability of failure. And I'm going to go through the benefits very quickly of this method. Basically, you have one method, and you can actually use the same method for different target probabilities. If you have performance-based design, you can adjust your target reliability, then it's very easily done. You could also rank your random variables. You can focus on the random variables that actually affect the end result. Focus on that. So, for example, your exploration would be focused on that. You can also highlight the cost of uncertainty. So that's a very big motivator for geotech engineers. They could do cross correlations for random variables. And then you can consider different distributions for random variables. And that concludes, these are some resources, and that concludes my presentation.
Thank you very much, Jomâa, for your presentation. I see no questions. Is this still the case from the audience? If you have a question, please feel free to submit it through the link.
I put some resources here for the audience, and these resources, the first one gives some suggested COVs, which is a coefficient of variations of different soil parameters. You can find a lot of information on this in the literature. Standard, an international standard that talks about this, it has an annex, is the ISO 2394, and the annex D there talks about this.
Okay, thank you,
Any more? Thank you. Thank you very much. That concludes my presentation.
Thank you. If there are no questions, then I guess we move on to the next presentation. is by Professor Zeghal.
Okay. Good afternoon, or actually good morning for some, depending on where you are. This presentation deals with the liquefaction and validation in geomechanics with a focus mostly on soil liquefaction models on the LEAP project. First, I would like to acknowledge my co-workers, Professors Manzari and Kutter, and my graduate student Goswami. I'm a professor of geotechnical engineering at RPI with a research focus mostly in computational geomechanics, including micromechanics and health monitoring of geosystems. After a brief introduction, I will present the LEAP project, followed by some results of LEAP 2015, then an overview of the plans for LEAP 2017, and I'll finish with some summary remarks. This is not moving. Okay, finally it's moving now. Soil liquefaction is a pervasive problem during earthquakes, as illustrated by the map of San Francisco showing the extent of liquefaction damage during the Loma Prieta earthquake. During earthquakes, saturated granular soils lose shear strength, which causes substantial damage to foundations, supported structures, and other geotechnical systems. Liquefaction reflects the particular nature of granular soils and the increase of pore water pressure due to densification during shaking. And numerous models have been developed to predict liquefaction and its effects. These models use finite elements, finite differences, and so on. These models are sophisticated. However, practitioners as well as researchers will not use these models if we don't answer the credibility questions, or in other terms, how credible are these models? A computer model is often obtained first by developing a mathematical model based on observations, and then the credibility of this model is established through an exercise of verification and validation. Verification is to make sure that the mathematical and computer models are consistent. Validation is to make sure that the computer model reflects reality and is consistent with experimental data from tests and observations. In this regard, LEAP, or liquefaction experiments and analysis projects, are collaborative efforts to build credibility in model predictions of soil liquefaction and associated effects. This is a collaboration that involves the U.S., China, France, Japan, Korea, Taiwan, and the U.K., and it's actually open to others if they would like to join. Specifically, the project is about verification and validation of soil liquefaction models using experimental results of centrifuge tests. And this involves the generation of reliable experimental data and establishing a formal framework for validation. A preliminary LEAP was conducted in 2015. It involved a centrifuge model of a sloping deposit of Ottawa sand tested in a rigid box at 6 centrifuge facilities. The tests were equipped with accelerometers, pore pressure transducers, and it's an extensive array, and I'll be referring later to the central array of sensors. The models were subjected to the tapered sinusoidal input motion that is shown at the bottom of the slide. The results of this LEAP, or P-LEAP, it's a preliminary LEAP, are being published in a special issue of Soil Dynamics and Earthquake Engineering. These are the achieved accelerations at the 6 different centrifuge facilities that tested the model that I was showing you, along with the input target motion, which is at the top. Some of the motions are similar and resemble the target motions, some are different. The discrepancies are due to differences in frequency, content, shape, and phase. The question is, which motions are similar and which motions are different? We need metrics to identify and quantify these discrepancies. These are the corresponding soil accelerations along the central array at 1.5 meter depth at the 6 different facilities. Again, there are similarities and discrepancies, and we need metrics. These are the corresponding pore water pressure time histories at 1 meter depth, and it shows that the soil deposit had liquefied during the shaking. One way of quantifying the overall discrepancy between two accelerations is to use a mean square deviation normalized so that it varies between 0 and 1. And that is given by the top equation. This discrepancy may be expressed as the sum of two components. One component that is a discrepancy in magnitude, the other one is a component to the discrepancy in phase. And the magnitude discrepancy can be decomposed further in terms of a shape component and a component associated with a shift in frequency. These decompositions can be done efficiently in the frequency domain. So, for instance, the magnitude discrepancy is obtained by comparing the Fourier amplitude spectra of the accelerations, and then the phase discrepancy is given by the equation at the bottom. And for the sake of time, I'm skipping the details of these equations. The discrepancy in magnitude stems from dissimilarities in shape and dissimilarities in dominant frequencies of the amplitude spectra. This is illustrated in a graphical form. So, for instance, the two signals that are showing are similar, but have large mean square deviation because the peaks and the valleys are at different frequencies. If we match the peaks and the valleys, we will get the discrepancies due only to the shape. We call this dynamic frequency warping because it's analogous to dynamic time warping used in speech recognition. And then we can get the discrepancy due to shifting of frequencies using the bottom equation. These are numerical examples. So here we have 3 numerical examples. In the first case, we have 2 accelerations that have only a phase difference. The total discrepancy as computed is equal to the phase discrepancy, and the rest are equal to 0, as expected. And then for the second case, we have 2 signals that have only a change in amplitude or shape. The total discrepancy is equal to the magnitude discrepancy, and the rest are equal to 0. And in the magnitude discrepancy is equal to the shape discrepancy. The rest are equal to 0. For the last case, we have a shift in frequency. The total discrepancy is about equal to the magnitude discrepancy, which is about equal to the discrepancy due to frequency shift. Unfortunately, I don't have time to get into the details why they are not equal and why the phase and the shape components are not equal to 0. Let me go back now to the input motions of the centrifuge test, and these are the total discrepancy among all input motions, including the target motion, presented in the form of a 3D graph. And it shows that F1, F2, and F3, these are facilities F1 to F3, they have input motions that have lower discrepancies than the other sides, which have larger discrepancies. The total discrepancy can be decomposed in terms of magnitude and phase components, and it shows that the discrepancies are mostly due to magnitude. The magnitude discrepancy can be decomposed further in terms of a frequency shift component and a shape component, and this decomposition shows that for signals F5 and F6 at facilities 5 and 6, they are dominated by the shape term. However, there's also a significant frequency shift discrepancy for these sites. And we use the same technique for the recorded motion along the central array at 1.5 meter depth. And the result shows that the facilities F1 and F2 have relatively low discrepancies among themselves. The same thing for F3 and F4. And there are large discrepancies for the other sites. The total discrepancy is due mostly to differences in phases among the signals, and the largest were actually for facility F3. This may be explained by the fact that this facility used a pore fluid that was more viscous than the other sites by mistake. This may give more damping, potentially. So this is a good way of trying to identify sources of discrepancy. The decomposition of the magnitude discrepancy in terms of shape and frequency components show that they are relatively low. The recorded motions were used in a Type A prediction by 5 modelers. Type A predictions means blind predictions. And here's the list of the employed soil liquefaction constitutive models by the different modelers. And this is an overview of the predicted accelerations by the different modelers along the central array, and they are compared to the recorded response at RPI or Rensselaer. The recorded motions are the top left time histories. The question is, how do we quantify and assess these predictions? These are the corresponding forward pressure time histories. Analysis of the accelerations and forward pressure time histories predicted show that there's a subset of simulations that are predicting reasonably well the measured response. The question is, how do we quantify and assess these predictions? This is work in progress, but what I can show you are some results that we obtained for a Type C prediction. We conducted the Type C prediction. This means a prediction that was conducted after model calibration using the open source code and the UCSD constitutive model. These are the recorded and computed accelerations along the central array from the input that is at the bottom all the way to the motion at 0.5 meter depth. The recorded motions are for RPI and Davis. They're showing on the left, and the predicted response or simulations prediction are on the right. Again here, how do we assess the differences and the discrepancies between the predicted and the recorded responses? So we conducted an analysis. This slide, this slide did not go. Okay, I'm pushing them now. Sorry for that. So we conducted a discrepancy analysis for the recorded and computed motions. So at the bottom, I have a comparison between the input motions and the target motion, and it shows that the discrepancy between the input and the target motions are relatively small, and they are due mostly to shape discrepancy. At 2.5 meter depth, these are the figures that are shown in the middle. The discrepancy between the model predictions and the recorded motions is comparable to the discrepancy between the recorded motions. In other words, the predictions are acceptable. They have more or less the same kind of discrepancy as the motions recorded by themselves. Near the surface, the discrepancy between the model prediction and the recorded motions is larger than the discrepancy between the recorded motions. So that means the prediction at this level is not as good as the one, let's say, at 2.5 meter depth. And the decomposition of the discrepancy shows that the contribution is coming mostly from phase dissimilarities. Is this a sensitivity issue, or is that the model needs improvement? For instance, the damping mechanisms may not be appropriate. The conducted LEAP 2015 analyses showed that the validation of soil liquefaction models require estimates of uncertainty in modeling as well as in experimental data. It also requires an assessment of the sensitivity of the modeling and experimental data to variability in input parameters. These issues are being investigated in the current LEAP, that is LEAP 2017. I can show you some preliminary results coming from this LEAP. So we conducted more centrifuge tests. Now we have about 16 replicas of the same tests that were done at different facilities in June and July of 2017. And the idea here is to cover a range of variations in input motions and soil relative density to assess the sensitivity of soil response to variations in soil parameters. Since whatever precautions we take in centrifuge testing, we will never be able to replicate the test in a realistic fashion. The outcome of these tests is being used to assess the sensitivity of the recorded response to variability in input parameters. And our objective is to develop validation tools and metrics that are going to be function of the discrepancy, sensitivity, and errors so that we can assess the validation of different computational models. Let me conclude with some summary remarks. So LEAP is an international collaboration to validate soil liquefaction models. In 2015, we got relatively good agreement between 4 of the input motions that of the tests that were conducted. 2 tests had a different input motion, mostly due to shape discrepancies. And then soil response near the surface was affected by significant phase discrepancies. In LEAP 2017, we are incorporating the sensitivity and discrepancy metrics into validation metrics. And I'll finish by acknowledging the NSF support and acknowledging the different LEAP teams. Thank you for your attention.
Thank you, Mourad, for your presentation and for being on time. I think we have 2 questions. I think we have time to address them. The first question is asking, is there a way to get the slides from these presentations? I guess it's really up to the ASCE and the presenters. So that would be a personal question to each one. Yeah, we have a response here that says a copy of these presentations will be available on the Geo-Institute YouTube channel next week. I guess that's it. I don't see the other questions. Do you see any other questions from, if you press the Q+A button on the top? Mourad?
Yeah, there is a question. What is the definition of liquefaction used in this analysis? Is it effective stress equal to 0? And was that measured to the required accuracy needed for the different models? Was also pore water pressure measured? Yeah, the answer is that the effective stress, the vertical effective stress equal to 0 was used as a measure of total liquefaction. and the pore water pressure was measured for all the tests. So we had a central array as well as left and right array, and they included pore pressure measurements. I don't see any other questions.
Yeah, I think that was the main question, in addition to the question about the slides. Okay, thank you so much, Mourad, for your great presentation. I guess we can move forward to the next one, image analysis systems and computational methods.
Well, good afternoon, everybody. Can you hear me? I need somebody to respond that they can hear me. Okay, thank you, Diane. My name is Roman Hryciw, and I'm speaking to you from rainy Ann Arbor, Michigan. And I'm pleased to share the floor today with Professor Jose Andrade, who no doubt is in sunny Southern California. And rather than reading that long title again, I will introduce you to some of my collaborators at the University of Michigan who are modeling a variety of the devices that we have constructed over the years, all having the purpose of preparing soils for image analysis. On the far right is Dr. Hyun-Suk Ohm from Samsung Corporation in Seoul, Korea now, and he's adjacent to our translucent segregation table. In the forefront is Ji Zhu from Tongji University modeling our set imaging device. And in the background is Dr. Junsheng Zhang, who is, as of last month, an assistant professor at Iowa State University. He's at our stereo macro photography system. On the left side there is a device that we've been working with for 2 decades now called the Vision Cone Penetrometer, and we're not going to say much about that tool today. And on the very far right, you might recognize those brass rings, and the word S begins with S is forbidden here. We call those items relics. Our objective is to eliminate them from geotechnical engineering laboratories. So I promised that I would only say one word here about the Vision Cone Penetrometer, and I only say it because to introduce image analysis. We've been working with analyzing images collected both in the subsurface in laboratories for, again, close to 20 years, and a tremendous amount of frustration initially with trying to analyze these images which were captured below the ground surface. But we learned an awful lot during these frustrations, which allowed us to really develop some laboratory tools that have given us very precise information about characterization of soils. I don't think I need to tell the current audience about all the problems that are associated with the sieve analysis test. You can read them here. They're expensive, they're time-consuming and energy-intensive, noisy, dusty, generate vibrations. By contrast, taking images with the camera and analyzing them is much faster, much less costlier, clean, silent, modern. But most importantly, in addition to getting just the particle size distribution, we can get so much more information, including shape, angularity, fabric, and soil color. So if we take a look at these 2 images, they represent the 2 extremes of the problems that are encountered in image analysis. The upper figure on the right is what an image might look like if we were to collect it below the ground surface or during, say, a laboratory test in the laboratory. And it's very difficult to interpret this image because it's a 3-dimensional assembly of particles, and we don't get to see many of the particles in their full frontal projections. At the other extreme, if we were to take that soil and spread it out on, say, a glass backlit plate, the problem there is we have to separate all the particles in order to have a simple image analysis program analyze these for their dimensions and their shapes. So what we have done over the years is developed 2 sets of tests, one called set imaging for particles 2 millimeters and smaller, and the other test called the translucent segregation table for particles larger than 2 millimeters. And the objective of both of these devices is to prepare the soil for the collection of the images and thereby allowing the analysis to proceed much quicker and much more accurately. So we begin with the set imaging test. It's short for sediment imaging, and again, it's for particles in the 2 millimeter to 75 micron size range. you'll see many references at the bottoms of my slides, and the slides will be available, so if you want the details of these tests, please refer to those references. The sedimaging test is essentially a long water-filled column through which the soil sediments down to a window at the bottom, and by sedimenting through the water, the soil segregates by size. And then a camera takes an image of that sedimented soil. And since we can't show animations, you'll just have to trust me that in the end, the image looks like what you see on the left side there. So that is about 6 inches in height and about 2 inches in width. And what you see there is, again, the segregated soil with the coarsest material having fallen first and being at the bottom. You'll note the colorful squares at the bottom of that soil column. Those represent the size of an image analysis area. And each one of those squares produces one data point corresponding to the size of the particles in that area. And those squares in 10 columns scan upward through the soil specimen, producing thousands of data points that are shown in the upper right of this figure. And then we take those data points and we sort them from largest size to smallest size and produce a full grain size distribution curve as shown in the lower right. So this is a soil that has a coefficient of uniformity of about 2, which is still considered pretty much a uniform soil. Here's a soil that is even more uniform. It's a basaltic sand from Costa Rica, very fine sand and very uniform, and you can see that the particle size distribution curve faithfully shows that. And here's an example of a soil that is more well-graded, coefficient of uniformity over 3, and again, you can see the results of this test. I point out that that red line is not a line connecting a bunch of data points. In the lower right, it is actually a lot of data points, so that's why it looks like a line. So the question, of course, is how does it compare to sieve analysis? And the answer is pretty good, and it's getting better all the time as our analysis techniques improve. The second test, called the translucent segregation table test, is for particles larger than 2 millimeters in size, and there are some references shown on this slide that you can refer to. And basically, this is a large light table. It's about 1 meter by 1 meter in size, and it tilts upward, and it has a series of bridges that run parallel to the contours of the light table, such that we introduce a soil specimen at the top of the slope, if you will, and those particles slide down beneath the bridges, and these bridges have ever-decreasing underpass heights as they go down the slope. So essentially it's like a one-dimensional sieve, but we're not sieving here for the purpose of identifying the sizes. The reason that we're doing this is to separate the particles in such a way that the little particles will not be able to hide beneath the bigger particles. And then you can see in the upper left of the slide that there are cameras mounted in the surface that will photograph the soil particles, and it will photograph those soil particles after we lower the table and remove the bridges. So you can see on the right side there, the particles are separated by size. But the one thing that is not done is we don't have to actually separate the particles from touching each other. Here's the actual image collected with this backlit translucent table, if you will. The next step is to threshold it to create a binary image of pure black for the particles and white for the background. And the key step in this process is now to identify each one of these particles as an individual particles without having had to manually separate them. And if you take a look at that cluster of particles in the upper left where they're all touching each other, surrounded by that red ellipse, keep your eyes focused on it as I click to the next slide, and you see that this process of watershed segmentation identifies every single particle individually. And since it does that, we can determine the size of each particle and its dimensions. And from that, we can generate a particle size distribution curve, shown by the red dots here. Now, the difference between this test and the previous set imaging test is that in this one, every one of the dots actually represents an individual particle, whereas in the set imaging test before, it wasn't getting the size of every individual particle. It was just getting a representative data point for the particles in that area using a technique called wavelet analysis that we've been using. So I failed to mention that before. Anyway, as you can see here, the triangles, the black triangles are the data from sieving, and the red dots are from our TST test. And the trend line is good, but the results aren't perfect. And the reason for that, of course, is because we're only seeing 2 dimensions of every particle, and we're not seeing its third dimension, the vertical one. And that's the smallest dimension, and that has some influence on the particle size distribution. So here, in this figure, we were only using the intermediate size, D2, if you will, to determine what the particle size distribution curve would look like. So, to solve that problem, we go to stereophotography, and here is a rendition of our tabletop version of it, but it's also usable with our large translucent segregation table test. And for those of you who are not familiar with stereophotography, 2 images are taken of a scene with the camera at 2 positions, somewhat apart horizontally, and then the 2 images are analyzed using simple, very simple geometry. It's amazing how simple really it is to generate a 3-dimensional representation of the particles. We write all of our own software, and this is really software that is very easy to write. Having now the full 3 dimensions of the particle, we can generate curves of not just the particle size distribution, but we can get sphericity, convexity, aspect ratio, things that the aggregate people really like. And most importantly, if you look in the upper left there, you can see that the data points for the sieve and the green line now, which represents the 3-dimensional aspects of the particle, match quite nicely. But what geotechnical engineers are really interested in are particle angularity, roundness, and sphericity. And it's because, really, our engineering properties are most affected by the corners of particles, how angular or how rounded these particles are. So sphericity is defined by many in different ways. We have found the simplest definition of it to be the aspect ratio, or the smaller dimension of a particle divided by the longer dimension, while roundness has a very traditional definition that dates all the way back to 1932, a gentleman by the name of Oettle, and it's defined as the ratio of the radius of circles fit to the corners of the particle over the radius of the largest inscribed circle, shown in red here. Now, most of you probably, when you need to report an angularity or a roundness, will go to silhouettes of particles and compare your particles to them. But what we have done is found a computational geometry technique that finds the circles that fit to the corners. And therefore, we can very rapidly determine what that roundness is for every particle in an assembly. And we don't have to go just particle by particle. We can analyze an entire tabletop full of particles very quickly to get what the distribution of particle shapes are in an entire specimen of soil. At the next level of complexity is when we have particles that are in an assembly. And this is now where we need to move to some advanced techniques in pattern recognition. We need to find those particles in an image that have their full projections visible. And again, it requires building of a library of particles, and therefore it's a little bit more complicated. So you can see here that we've got all of these particles, and what this has allowed us to do now is, based on really excellent statistics, develop equations for soil properties, such as the maximum void ratio, the minimum void ratio. And you can see in my next slide that the agreement between measured values and predicted by our equations are pretty good. We have similar equations for compression index of soils, shown by the equation in the lower left. And here again is a comparison between measured and predicted values. So Professor Jose Andrade will be talking more about discrete element methods, but here is one way that we approached this problem. We wanted to simulate actual soil particles in an actual soil, and we know that what affects particle assembly behavior, soil mechanics is really the corners of particles, the angularity. So when we wanted to create a discrete element particle, we preserved those corners that were found by our definitions of roundness, and we filled the rest of the particle with circles that are tangent to the perimeter of the particle. And this created what is called a cluster particle that could be used in discrete element modeling. And if you can do it in 2 dimensions, you can also do it in 3 dimensions. And I didn't think we were going to have an animation, but there it is. Maybe you can see the particles now turning, showing you it from all sides. And my last slide here shows you that what we have done is created a library of these cluster particles, over 100,000 in 2D and another 100,000 in 3D, so that if you have your desired particle size distribution, particle roundness distribution, and sphericity distribution, we can sample particles from our library and feed it directly into a discrete element model and faithfully, therefore, perform a model analysis on an exact replica of a soil that you collected from the field. So that is my last slide, and maybe we'll wait until Jose finishes with his before we answer questions. So I'll maybe turn it over now to Jose.
Thank you, Roman. That was a great introduction to particle shape characterization and how to go from an image to a model. Good morning, everybody. For those on East Coast time, good afternoon. Good morning to those on Pacific time. Good afternoon to those in East Coast time. My name is Jose Andrade. I chair the Computational Geotechnics committee. It's a pleasure to be here. I'm also a professor at Caltech. And one of the things we do is we take images and we are interested in making them computational models. And today I'm going to be showing you how you go from the kind of characterization that Roman was showing us in the lab to actually creating a computational model that can be believable and that can actually represent reality of soils. So my title is slightly different. It's All You Need Is Shape. And here we're going to be taking images and making them into computational models or DEM models. So Roman showed many techniques based on taking pictures. Another way of taking pictures of soils is to do X-ray computed tomography. This is work in collaboration with our partners in France. What you see here in front of you is a tomograph, and you see that there's an X-ray transmitter, and in the middle or in front of that X-ray transmitter, there is a triaxial cell with a sample there. You can see the membrane, and that sample is going to be compressed triaxially in the classic way that we shear soils. And in the back, there is an X-ray receiver that captures the X-rays that are being attenuated after they've impacted the specimen. And to the very far right, you see a slice of a typical two-dimensional slice in the specimen, but then they stitch together all of these slices and reconstruct a three-dimensional image of a sample. So X-ray is a proven technique to be able to capture these pictures that Roman was showing us earlier and stitch together pictures of samples in 3D. So it allows us to look inside of samples, but more importantly, these are samples that are being also sheared in the triaxial chamber at the same time. So we are taking pictures while we are deforming the sample, and that's going to be invaluable information for computational models. But you can take your favorite imaging technique and everything I'm going to present today will also apply. So one of the questions that we have attempted to answer here, given the interest there is in imaging now, whether from a picture or from X-ray, is how do you go from a picture to something quantitative that you can then use in a model, and that we call level set imaging. And so here we're going to be using level sets instead of clusters of circles, as Roman was showing earlier. Here we're going to use level sets, and I'll explain very briefly what level sets are. But the idea is to go from a picture that is typically voxelated or binarized to a mathematical description or some sort of description of shape of a particle. So here's an example of a silhouette of a particle in 2D. You can also do this in 3D. Everything I'm going to show you later is 3D. But so here's my raw image. Maybe it's a picture. Maybe it comes from an X-ray CT. And what I do is I then go from that picture and we compute gradients, and also we use the watershed method to be able to individually separate those grains. So you got to give your grains identity, and also you got to figure out where the border or the boundary of your grains are. And then once you know where the boundaries are, you can come in with level sets, which is nothing but a contour map of the distance to the surface of the particle. So here you can imagine those that took surveying, which is most of us that have a background in civil engineering. These are contour maps. Instead of being elevations, you can see them as contour maps of distance. Inside of a particle, you're going to have negative values of contour map. Outside of a particle, you're going to have positive values. At the particle boundary, you have exactly 0. That defines the shape or the boundary of your particle. So you can do this for every single particle extremely fast. So for every particle, there is a level set. And this is the result or the main example here with 3 different types of sand. You can see that they range in angularity. So we have the classic Houston sand, Caicos ooids that are more rounded sand particles, and then the classic Quikrete sand as well. And you can see that the bottom images are not pictures. Those are level set representations or mathematical representations of these shapes. And so at this point, those particles that have the full resolution that you had in your images have exact representation ready to be implemented in that discrete element model. So the other remark I want to make at this point is that you don't need a picture all the time. You can do, as Roman was saying earlier, you can go from particle shape distributions and some characterization of shape or morphology, and you can go into a library where you can pick particles that match your particle size distribution, the shape distribution, and also the number of particles that you wish to have, and then you can create a discrete element model. So the big vision here is that we would like to go from an image onto a full model of a specimen, and we would like to make a direct comparison, the first direct comparison between a triaxial sample of sand being sheared as we're taking pictures of it, and modeling the exact same triaxial sample with the same particles, because we know each of the particles from the X-ray CT, and the same boundary conditions, the same pressure, the same radial pressure applied to the membrane, and the same axial deformation. And we would like to compare and see if the discrete element method or the discrete element model is able to capture the experimental results. So here I'm going to show you an example of how we go from a full specimen that you can see here in the 2D X-ray CT slice to a three-dimensional computational model. And these are small samples. They're about 60,000 grains in the samples, so that they can take X-rays of them. So are these models any valid? Can you compare well with DEM? So here I just want to compare with the classic DEM and LSDEM, the level set DEM. So we can take images through the LS imaging process and put them into a DEM framework. This is what you could call meshing in the FEM world, right? You go from an image to a computational model. And then the similarities is that both methods track individual particles, and the time integration algorithms are exactly the same, and the boundary conditions are exactly the same between LSDEM and classic DEM. The only differences are that the shape representation, of course, varies, right? LSDEM represents shapes with level sets, and it can do arbitrary shapes, whereas the classic DEM can only do circles. And the computational cost, of course, is slightly higher for LSDEM, but I want to remark that it's not terribly higher. And we know that shape matters, as the previous presentations have shown. Okay, we have these two metrics of roundness and sphericity for shape, and depending on where you are on this spectrum, properties are going to change, in particular strength, and we know that, and we have characterized that very well. So, for instance, we know that shear strength will increase as roundness decreases, and also sphericity increases. So capturing shape is something very, very important. My next slide, I will apologize in advance. I don't think it's going to display well. The platform doesn't support videos. But this is a two-dimensional shear study showing the effect of particle shape at critical state. But here's the upshot of that. As we vary, again, we're on this same map of roundness and sphericity. As we vary roundness and sphericity, we see that we have a decreasing angle of friction at critical state as the particle becomes more round and more spherical. And the opposite, of course, is also true. As we drop roundness and sphericity, we increase the angle. And that variation in angle is not insignificant. It's about 10 degrees. So shape matters. And so here we go back to our study, our three-dimensional study that I want to show you about. So this is the first one-to-one comparison between an experiment and a computation. Every grain has its own grain in the computation, every grain in the experiment. It's triaxial compression, and we want to see if we can capture microscopic behavior, also the onset of localization or the shear band, and also if we can tell anything about the particle kinematics. So we're going to look at all three of those. And again, this is another failed video, but I'll just advance to this one that I think will show. So there you see a movie of the two-dimensional slide through the center of the sample, and what you saw were the vertical displacement map that we see as we compress the sample. And you will notice from these images that the platen is allowed to rotate, and that was captured also in the model. The platen is only prescribed the vertical displacement, but the rotation is free, so that the platen can rotate at will. And we're prescribing here the confinement that was 50 kPa, which is the same as in the experiment. So I think these are the most interesting results. And next one's here. So this is a comparison of the macroscopic low displacement result showing the stress ratio, sigma 1 over sigma 3, versus the axial strain for both the experiment and the computational model, the DEM model. And the same for the volumetric strain or the volume change versus the axial strain. These are classic results that we get from triaxial compression tests, and you can see that the experimental data is right on top of the computational results, and this is what we would call a type C prediction, right? Because we did calibrate the DEM parameters such as stiffness to be able to replicate the parameters, but you can the results rather. But you can see that the similarity is remarkable. The model does a really good job at capturing that latency. So, okay, so far this is what continuum models can do at this point as well. But for instance, here is something more challenging that continuum models cannot do. So here is a plot of the experimental results in terms of deviatoric strain. So these are 4 different snapshots. Those 4 columns you see in yellow are 4 different snapshots of the deformation or the deformed state of a sample during 4 different times in the experiment. So at the beginning, around 5% axial strain, and 10% and 15% global axial strain. And you can see that there is a shear band in the middle in both the sample and the computational model. And you can see that they appear at the same location, and the thickness of the shear band is about the same, but also the amount of shear is the same. So at the local level, the strains are being predicted incredibly accurately. And this is something that definitely no continuum model can do. This is a plot at the same stages of deformation, but now we're looking at incremental particle rotations. So how are these particles rotating? Mostly the rotation happens inside of a shear band. And you can see that both the experiments and the computations match quite well in terms of the amount of particle rotation. So I think this is convincing evidence that these methods are able to replicate reality in particular experiments. Here is just the force chains, something that we can see in these models, but we cannot see computationally. And this is one of my last slides. This is cyclic loading. I won't be able to talk too much about this, but this is a test where we loaded and unloaded a sample of sand, and we did the same thing computationally. This is a class B prediction because the parameters were calibrated in the previous example, and you can see that you can essentially not tell the difference between the experiment and the computation. So it's producing very interesting results, and these are just snapshots at different levels of deformation, here showing extension. So we were able to go into triaxial extension and get something that I have never seen in soils, at least in granular soils before, which is necking. You see quite a bit of necking at 15% axial strain. And here is a small inset of the same picture in the experiments where they also saw necking. So that was my last slide. With that, I would like to conclude and just summarize that we have imaging techniques like those that Roman showed before. So you can take pictures or do X-ray CT, and from that you can create models that I hope I have shown you can replicate experimental results quite nicely. And we're quite excited about that because we can then use those to make Class B, Class A predictions and improve our knowledge of soil parameters, which one of the earlier presenters said was one of the most significant sensitivity sources and issues in calibrating models for liquefaction prediction. With that, thank you very much for your attention.
Thank you, Jose and Roman, for your presentations. We have 4 questions. So could you please go to that question and answer this?
Okay, so I guess I'll take these 4 questions. So I'll start with the bottom one. Are the individual grains considered undeformable and infinitely strong? The answer is, in this particular version of LSTM that we have implemented, they are undeformable. You know, there's a tiny bit of overlapping, but you could have a different version of DM if you want to account for deformability. The method allows you to do that. The next question says, does LSTM consider any fluid, air, water between the particles? At this point, we're not considering the effect of fluids, but that is something we are working on. The next question is, the necking under tension indicates cohesion. No, that is the effect of the membrane. Remember, this is a triaxial compression and extension test, so there's a membrane around the sample, and that's why the sample is allowed to remain coherent, if you will, even though there is necking, and you can see it in the experiments, and you also saw it in the computation. So there's no cohesion whatsoever. That's why it's so interesting to see necking. Okay, and I think the last one should be for Roman, because it's a question on how the presence of clay impact these visual assessment tools.
Sure, thank you. So if the question is in regards to the test that we call set imaging, we have a way to get the percentage of fines in order to classify the soil. And it's written up in our paper. Basically, we drain off the water that still contains the clay before we take the image. And I'll just take the opportunity to mention that if there are no fines in that particular test that we call set imaging, we never have to use a scale to weigh the soil, and we never have to use an oven to dry the soil. And these tests are extremely quick. In fact, right now we're working on a project where we hope to run as many as 25 to 30 tests per day to characterize a riverbed over a distance of 7 miles. So it's a very rapid test that doesn't require, weighing, and it doesn't require drying. But again, we cannot do the clay. We can only get the percentage of fines at this point, but we can't give you a particle size distribution below the 200 sieve.
Roman, I think there is another question. I don't know, maybe you don't see it. It says, are there currently any commercial laboratories using these methods?
No. If the question is about mine, no, there are not.
Okay.
Usama, just a quick comment for those interested in the movies that unfortunately didn't play. I guess when they are posted on the YouTube channel for the GI, those movies will show then, and you will be able to access them.
Okay, thank you so much. So we move on to the next presentation, which is actually my presentation. So once again, my name is Usama Shamy. I am an associate professor at Southern Methodist University in Dallas, Texas. And I would like to welcome everybody to our webinar today. I am also the vice chair of the Computational Geotechnics committee that is organizing today's webinar. My talk today is about seismic soil foundation and structure interaction and new insight. So basically, the problem of seismic soil structure interaction is an old one, and the interaction among the structure, its foundation, and the soil medium below the foundation alter the actual behavior of the structure. And the methods that are available, as you might be aware, that are available to analyze these systems are direct methods such as the finite element method, the boundary element method. These are the common ones or mainstream ones. Also, substructuring techniques, which are uncoupled techniques. And What I'm trying to present today is a new modeling technique that try to account for some of the challenges in modeling, such as soil nonlinear behavior, soil inhomogeneity, possible separation between foundation, base, and soil, foundation shape and embedment, dynamic soil foundation interaction, as well as the dynamic characteristics of the structure itself. As you may know, accounting for all these factors in one technique, in one computational technique, is quite a challenge. So you heard from the previous presenters a little bit about DEM, and this is what I'm going to rely on in my models in my model today, the discrete element method. It's a powerful tool to model granular materials and capable of capturing the complicated behavior of actual materials with relatively simple assumptions and a small number of parameters at the microscale level. In addition, DEM simulations provide a great deal of information at the microscale level, so if you want to know particle rotation, particle contact forces, you can get that, as well as at the microscale level, things like stress, strain, behavior, we can also retrieve that, as you have probably noticed from the previous presentation. So I'm not going to present a lot of details in terms of equations and things like that. All you know for now is that discrete element models any granular material as a collection of particles. So in order to do a microscale framework for a soil foundation structure system, I have this hypothesis that the soil deposit itself is a collection of unbonded particles. The footing is made out of particles, but they are glued together or clumped together, so the entire foundation behaves as a rigid body. The structure is made of a bonded particles or clumped particles, depending on whether we want to model a flexible structure or a rigid one, with a lumped mass on the top. That's a very classical way of presenting a structure. The advantage of doing that is that the model inherently accounts for soil nonlinear behavior reflected by the movement of particles. So as you probably have noticed from the previous presentation, really nonlinear behavior here comes from the rearrangement of particle position and the sliding of particles, and as well as rotation. That is the main source of nonlinearity using these DEM techniques. So there is no need for any additional parameters as in continuum models to do the same job. Also, the random generation process of particles composing the soil deposit produces a system that has a spatial variation in properties. So inherently, it accounts for soil inhomogeneity. The model accounts for nonlinear soil foundation interaction through a near-realistic idealization of the surface of the footing interacting with the particles. So there is no need for special interface elements. That's really what it means. Modeling the structure as a member connected to the foundation block that is resting on the soil deposit allows full coupling between the structure, its foundation, and the underlying soil. So what we are about to see is a time domain analysis of the seismic response of soil foundation systems using DEM. So this is a snapshot of the final product, meaning the soil deposit resting on a rigid bedrock. That's a rigid wall that represents a rigid bedrock. And then the foundation embedded. It can be also on the surface. And the particles composing and representing the structure. Professor Andrade, in his previous presentation, he mentioned that he was dealing with simulations that had about 60,000 particles. So, of course, if we go to a system like this, we try to model now large-scale problem, you are expecting a significant number of particles that current computational power may not be able to handle within a reasonable time frame. So in order to do some in order to overcome this challenge, we use some tools available to us. One of them is using the high gravitational field that is used in centrifuge testing. We heard a little bit about centrifuge testing earlier today, and the idea is by presenting or subjecting the system to high gravitational field, you preserve the stress level in the soil deposit to values that are similar to a prototype, meaning a field condition or an actual field condition. And by obeying certain scaling laws, you can always, find or scale down your model to a manageable size. So with that, we were able to scale down the size. We also scale down the time of the simulation. So if we subject the system to certain earthquake motion, instead of using the actual time, it's scaled down by 50 in this case. And in order also to mimic or to eliminate any effect of boundary conditions, lateral boundary conditions, we use periodic boundaries. And the effect of these periodic boundaries is that it's like we are modeling really a replicated system in the two lateral directions, a system that is repeating itself. We just take one, and the idea here, or the numerical tool here that is allowing us to do so, is the wave that reaches a periodic boundary. It doesn't reflect back. Instead, it continues propagating in the adjacent system, and another wave enters from the other side. These are some simulation details to show you, kind of how simple the parameters that are needed for this. I'm not going to get into a lot of details about them. Also, before we start discussing any results, we would like to get some idea about what we're dealing with here as a deposit. In these simulations, my particles are perfectly spherical, so I'm modeling a well-rounded sand grains, if you wish. So the phi angle is about 26 degrees in these simulations, as came out from a consolidated drain triaxial test. We wanted to also get a feeling what is the shear wave velocity. So at low strain, we were able to measure the fundamental frequency of the system. It was about 7.6 hertz. Pay attention to this number. That the fundamental frequency in terms of shear wave propagation is 7.6 hertz, and this corresponds to shear wave velocity of 125 meter per second and a low strain shear modulus of 26 megapascal. In addition to that, because as I will present in a minute, the simulations will also account for vertical excitation, vertical wave propagation. So we needed to know a little bit more information about P wave velocity, and by doing a numerical simulation of a vertical impulse propagation, the compressional wave velocity was about 220 meters per second, and that corresponds to a fundamental frequency of 13.75 in the with respect to vertical wave propagation. With that, we are ready to tackle the main subject is to model seismic response, and we are accounting here for multi-base motion. And there have been a lot of studies to tackle this problem, but very limited accounted for the vertical component of of earthquakes. So we try to shed some light on this issue using this technique. So we perform a number of simulations. We start from unilateral base motion, and then we also look at 1D vertical base motion, and then bilateral base motion, and end with the 3-directional base motion. There are a lot of information that we can get from these simulations. I'm going to focus on motion amplification and foundation settlement here as key response. So this is the amplification factor resulting from subjecting this deposit to different sinusoidal motion with different frequencies, 2 Hertz, 3 Hertz, 4 Hertz, and 6 Hertz. As you may see, the largest amplification factor was associated with the 6 Hertz frequency, and that is because that is close to the 7.6 Hertz fundamental frequency of the deposit. So you get, closer to resonance, and you get large amplification factor. And down there is some comparison with the analytical method that I'm sure all of you, if you have Professor Steve Kramer's Geotechnical Earthquake Engineering book, you can refer to and use this analytical technique. There is some decent comparison right there with the results of that method. So the foundation settlement under the effect of unilateral motion is that the largest settlement was again when the excitation was close to the resonance frequency. All this still unilateral motion, and then we shift our attention to only having one vertical base motion. And we had a sinusoidal motion with frequencies ranging from 2 Hertz to 20 Hertz. So we are spanning the natural frequency with respect to vertical excitation with these values. And this is the amplification factor in this case. And you will notice again that is the largest amplification was that at frequency of 12 Hertz. It was close to the 13.75. Again, comparisons with the analytical method are fairly good. We increase the amplitude of motion. The previous slide was the maximum amplitude of the motion was 0.1 G. Here we increase it to 0.5 G. And what we notice that really the amplification factor values didn't change much, except for the one that was near resonance. That was had a significant deformation. That's why it's not shown in this slide. As far as settlement, settlement was relatively small under vertical motion, and only again the case when the frequency was 12 Hertz, we got a settlement of about 33 millimeter. Then we move on to examining the effect of bilateral base motion. So we take our structure and its foundation and the soil and subject it to different base motion. And we have circular motion, we have this butterfly shape. And this is a snapshot of the computed soil planar acceleration at near the surface. So we see that for the circular motion, it was pretty much preserved. The shape of the motion continued to be circular, but for the butterfly, especially when the frequency of the each direction was 3 and 6 Hertz, we got distorted shape, and that is because the amplification in each direction was different. The 6 Hertz was close to the resonance, so it had higher amplification than the 3 Hertz. And that is clear from this profile, that the different directions in the case of the butterfly motion with 3 and 6 Hertz in each direction had different amplification profiles. As far as settlement, as you may expect, settlement using 2D shaking is larger than using only one component. The settlement under bilateral base excitation was about 10 to 30% smaller than the sum of the settlement caused by considering the 1D components acting separately. So if you go and use, like just sum the 1D, you are on the conservative side, if you wish. Then we move to our target, which is modeling the 3-directional base motion. So we subject the system now to a vertical excitation in addition to the 2 lateral ones. And what we notice is that the impact of including the vertical motion on the horizontal motion amplification is only when it's near resonance, the 9 and 12 hertz. When the vertical excitation is near resonance, you get higher amplification as opposed to ignoring the inclusion of vertical excitation. These are the different amplification factors for different directions, and the conclusion here is that the inclusion of lateral motion did not have significant impact on the amplification of the vertical input motion. When we look at settlement of the foundation, only the effect of including the vertical excitation was only important or had a significant impact when the frequency was 12 hertz. The frequency of the vertical component was 12 hertz, and that is because it's close to the resonance frequency. In that case alone, it increased the settlement by 2 times compared to ignoring it, compared to only having the 2 lateral components. We also wanted to see if we can examine, actual earthquake record. So we took the 1979 Coit Lake, California earthquake as an example. We did some response spectra for the accelerations to find out the predominant periods of this earthquake. And we started running the simulation, and we found that the response spectra for bilateral motion was smaller than that of unilateral base excitation. And we did the same thing for the vertical component. We found that it didn't have significant impact on the response of the soil if we add the vertical component. The foundation settlement for that actual earthquake is that we noticed that changing the frequency content of the vertical motion did not have significant impact on the settlement, and increasing the amplitude of vertical motion increased the magnitude of settlement. We did some scaling of the earthquakes so that we can see the effect of frequency and maximum amplitude, and that was the conclusion that increasing the amplitude of vertical motion increased the magnitude of settlement. For the sake of time, I don't want to go through more slides, but I wanted to show that quickly that we can also eliminate the base rock and use absorbing boundaries if we want to have elastic base or infinite media as done in classical techniques. And that, of course, will have significant impact on the response. I mean, if you have infinite medium now, the foundation settlement will decrease significantly because your system will shift away from resonance, and the behavior will change dramatically. So, in summary, the seismic response of soil foundation structural systems subject to multi-directional base motion was modeled using this DEM technique. The technique is capable of simulating different boundary conditions such as rigid base, elastic base, and infinite medium in multi-directions. The vertical motion amplification was independent of the intensity of input motion. The vertical motion amplification under the structure increased compared to that of the free field. The presence of vertical motion did not have impact on the amplification of horizontal motion, and the lateral motion had small impact on the amplification of vertical input motion. And lastly, the vertical motion did not have impact on settlement of foundation for frequencies that are far from resonance. With that, I would like to thank you for your attention. This is a reference. If you want more information about this presentation, you can always refer to this ASCE publication. Thank you very much for your attention. I guess there is one question. Try to see it. Well, yeah, thank you. So I guess we move on for the sake of time to the next presentation.
Okay, great. My name is Nick Oettle. I'm a geotechnical engineer at AECOM. Let me see if I can pull up my slides. Okay. I think everyone should be seeing my slides now. So my presentation is on a set of guidelines that the Computational Geotechnics Committee would like to develop. These guidelines have not been developed and they have not been started yet. So this presentation is an outline of what kinds of issues we might address in a set of guidelines for best practices doing geotechnical numerical modeling in industry. And I'll conclude this presentation with an invitation to you to join this effort and help develop these guidelines. I'm attempting to go to the next slide. Okay, there we go. So part of the motivation in developing some guidelines for numerical modeling in practice is that guidelines are really important to how geotechnical engineers work in practice. We've got guidelines for everything. We've got really great guidelines from entities like AASHTO and the FHWA and NAVFAC for a lot of typical technical topics in our industry. One of the really best guidelines, in my opinion, is actually a very short and sweet suggested guidelines document written by an A.S.CE technical committee for geotechnical baseline reports. And it's extremely respected and used all the time in the area of tunnels and underground construction. And it's really a consensus among practicing engineers of what the best practices are for writing GBRs. It's not technical in nature. It's qualitative and provides guidelines of what a lot of the most experienced engineers have through successes and failures found to work well. And we really don't have almost anything like this in the field of numerical modeling. There really aren't any guidelines to sort of help develop an industry consensus of what a best practice is for numerical modeling. And so this effort is to fill that void and present some consensus guidelines. I've done lots of numerical modeling in industry, both myself and by reviewing other numerical models from within my own companies and by reviewing models from other companies in many states in the United States and for overseas projects. And I can tell you that the current practice varies very widely. We've got engineers with bachelor's degrees who don't have really any educational background in numerical modeling, doing numerical models, all the way up to people with Ph.D.s who did research in numerical modeling and have published papers on it. The sophistication of the kinds of models that are used in industry varies all over the place, everything from very simple steady-state seepage analyses for flow nets under sheeting to very complicated fully coupled nonlinear analyses for earthquake applications and dams. The software that's typically used in industry, in my experience, is almost always closed source. I've never seen open source used, even though it would be a great idea, I think. Most of the software is, Tasica's FLAC and Plaxis and similar codes. Documentation that people produce in industry ranges from basically nothing to very detailed reports, detailing calibrations of parameters and really getting into the details of results. Peer reviews are a really important part of engineering in general, but it varies a lot for numerical modeling because there are some particularly difficult aspects for reviewing numerical models. I often see no reviews done at all in numerical models, and occasionally we have many reviews, even with a panel of experts looking over the results. And at least in my experience, I have seen some models that have been done by somewhat competent engineers and checked and we have really completely nonsensical results. I've seen a situation where people were trying to get some parameter at some location in a model, and it was exactly where their boundary condition was, and they're basically feeding themselves the answer. And I've seen very high-quality numerical modeling done, doing things that you really can't do with simple analytical, empirical models, and doing really good engineering where numerical modeling is really advancing our field. So what I'm going to present here today is really a series of questions of what kinds of things we might want to develop in these guidelines for what we feel good suggested practices would be for numerical modeling. These aren't answers. These are a series of questions. And so one is validation of these models. And just ignore the titles on these slides. I flipped them for the next two slides. But this is validation. And a really important part of numerical modeling is making sure that we validate a particular model that we have against reality. So would you want to use more Coulomb for site response analysis if you expect a really nonlinear response? Probably not. These guidelines would not address specific technical issues like that, but rather who should be responsible for validating models. A lot of constitutive model developers, such as in academia, would do a lot of this kind of validation, as we saw previously in one of the previous presentations. For example, someone developing a model like EB-SAN might check that it can do a reasonable job of estimating dam deformations when you have liquefaction in the foundation. Software developers like Itasca might do some of this as well when they implement their own model in their own code. Can we model a well-known case history and get reasonable, consistent results with that case history? And sometimes the end user even does this. The practicing engineers who have to stamp and rely on these models for engineering, they might want to validate the model to make sure that it's okay. Who should be responsible for it as a good practice, or should a combination of people be responsible? A similar thing for verification. Again, the title is switched on these. Are there bugs in the software? Are we correctly implementing the model that we think we are mathematically in the software? My company in particular has made a push recently to try to have us verify all of the engineering software that we use. And so you can imagine that's a big undertaking when you're talking about a very complicated closed source software where we can't really read the code that's actually being executed. We would have to develop a lot of models and test cases to see if whether we're getting the output that we expect for, say, a 1D linear elastic model where we put some stress on it and we see if we get the right strain. Should we be responsible for that? Should the software developers be responsible, or some combination? What is a good industry practice is the question. A really big, somewhat contentious issue is qualifications. So we have everyone from people with undergrad degrees, MS degrees, Ph.D.s doing this work, different years of experience, classes, research experience. Lots of people with master's degrees have one class in, say, theoretical finite element analysis, where they covered the mathematical aspects of, say, a B matrix and how to solve linear elastic problems of, say, a steel plate with a hole in it, to try to calculate stress concentrations around it. And then there's really the whole separate aspect of constitutive modeling, which is really a core component of geotechnical analysis, understanding the advantages of limitations of using a more Coulomb model versus, say, a modified Cam-Clay model, depending on what you're trying to model. So if you want to have a good chance of getting good quality results out of your numerical modeling, who should really be running these models, who should be reviewing them? It probably depends a lot on what kind of model you're running, anywhere from simple steady-state seepage analyses to very complicated numerical models. Documentation is really important in numerical modeling and engineering in general. It's often the means by which the results are checked. So another engineer reviews what was done, what parameters were assumed, how they ran the model, and whether the results make sense. It's also how other engineers and parties understand what was done, what was assumed, and what the results are, so that we can coordinate and work with other engineers on large projects. It's the way that results are repeated, like if one company does a model for a preliminary design stage and another company gets the contract to do detailed design, they might want to understand what modeling was done previously, how they did it, what they assumed. And it's the way that results are archived for long periods of time if we need to go back years later and understand how some infrastructure was designed for and what it might be able to withstand in the future. And there's so many options for documenting numerical models. We have automated software output. That's great because you can click a button and all of a sudden tons of input and output is spit out into a PDF that you can attach as an appendix. Usually most engineers will write some description of what they did in a report, like a geotechnical report, of varying detail. Some are extremely long and detailed and go into every little detail of how the numerical model was done. But what's really a good practice? If we wanted to do a good job documenting our models, what would we really do? Automatic output versus describing our calibrations. What's a good practice for different types of projects, low-risk ones, medium-risk ones, high-risk projects? Interpreting the results is always a key issue. Many engineers in industry and in practice don't really believe in numerical modeling and don't really believe the results. And part of the issue is you run a numerical model and you get some results and you really don't know if it's the right result, if it's going to reflect reality appropriately. And so many engineers address this in various ways. You can run multiple constitutive models if you're not sure you're running the right constitutive model. Some people will even run their models in one software, and then they'll take one or two key cases and run it in a completely different software package to see if they get similar results. You can vary parameters just like you would in typical analytical engineering situations. That can be more hard with finite element analysis because it's more time intensive to run separate models over and over again. And of course, for most situations that aren't trivial, you would almost always check your results against an analytical solution or empirical models as appropriate. If someone is running a numerical model of a deep excavation, almost everyone is going to check the deformations against something like Clough and O'Rourke. So what's a good practice for this? For low-risk projects, maybe you don't need to check it other than checking it against your own experience for what you think a reasonable result would be. For moderate or high-risk projects, it might involve one or two additional checks. For really high-risk projects, you might run separate constitutive models or separate models entirely. These are the kinds of things that we might address in these guidelines. Peer review is really important and a little bit tricky for numerical modeling. There really isn't, in my experience, a really accepted practice for peer reviewing numerical models. There is for just about every other kind of engineering, but in numerical models, it's really hard to review other people's models because there's a far more limited amount of engineers who have the requisite expertise to be doing engineering, and the models themselves can be very sophisticated and complicated, and it takes a lot of hours to really get into someone's model and figure out why they modeled it this way or that way. And in industry, everyone deals with limited budgets. But reviewing is so important. What can we do to try to make the review process work better and more consistently in industry? Should it involve reviewing someone's native files and actually opening up their modeling runs to look in detail to make sure that there aren't errors where some node isn't connected to another node? Should there be independent replication of results for high-risk projects where we give some basic geometry and parameters to another engineer to develop a completely separate model to see if we're getting similar results? So the proposed scope that we would like to have for a publication of good guidelines that the committee would like to develop is really to improve the quality and consistency of numerical modeling in practice in industry. This would not be a textbook. This would not cover technical details. This would be relatively short and cover broad issues like validation and documentation, peer review, such that someone who is maybe an office manager at a consulting company, and maybe they're not even a geotechnical engineer or they're not even numerical modeling, they have a big project where they need to do numerical modeling for something that could be a high-risk venture for their company. Someone who is an office manager could say, I would like you to follow these guidelines, and if they recommend something for peer review, let's do that. If they recommend something for verification, let's do that. Let's make sure we do these things the right way so we can have a better chance of getting good, reliable results, and so that geotechnical engineers and other engineers throughout industry see numerical modeling as something reliable and something that provides good, valuable input for their projects. So, if you are interested in improving the quality of numerical modeling in our industry, I'd be very happy to hear from you. We would like to develop a group of people who are interested in developing a consensus for best practices in the industry. And so that concludes my presentation. I would be happy to answer any questions if they come up. Now I'll look in the questions area to see if there's anything. I do not see any questions. So I'll hand it over to Usama to wrap up this webinar. Thank you.
Thank you, Nick, for pressing on so many issues in computational modeling and making these great points. So there are no further questions related to any of the presentations today, I guess. So I would like to take this opportunity to thank everyone who attended today. I hope you enjoyed our first webinar. And I would like to thank all the speakers for their great presentations and being on time, and for their great work as well. Thank you so much, and we hope we see you again. Bye, everyone.
Thank you. Ladies and gentlemen, this does conclude today's webcast. We thank you for your participation. You may disconnect your lines at this time and have a great day.